Hey everybody, it's Mr. Carr again. Today we're going to be starting Unit 2 about quadratic functions. So today's goal 2.1 day 1, we're going to be graphing quadratic functions that are in standard form. So what is standard form? Looks like this. Okay. So a function with an x squared term is called a quadratic. Whoops. Place there. Okay. It is called a quadratic function. In this format right here, where it's y equals ax squared plus bx plus c, this is what's called standard form. That's what this one is right here. So the graph of a quadratic function forms a U-shaped curve called a parabola. Okay. Now, just like we've done in the past, we're going to look at what's called the parent function of a parabola, or a parent function of a quadratic. And that's just y equals x squared. Notice it has symmetry, just like when we did our absolute value functions. It also has a vertex. So in this case, my parent function's vertex is at 0, 0. There's a special thing about this called the axis of symmetry. It's the axis or the line of symmetry. This is a special line that cuts it right down the middle, so we have this mirror image on both sides. So just like with our absolute values that has the V shape, now we get this U shape here, and we get the same thing on both sides of that line of symmetry. So in this case, it's the equation x equals 0 for our parent function. Okay, so again, this is the equation of a vertical line. All right, so that's why we have to write it as x equals. The vertex is a point on the graph. So that's why it's an order pair of x comma y. Okay, so some more characteristics of our quadratic function. If it opens up, that means this a value is a positive number or it's greater than 0. And so when I say opens up, it means it looks like this. If it opens down, that's when a is negative or less than 0. So a parabola that opens down just looks like this. So we got a valley versus a hill. If the absolute value is greater than 1, it's vertically stretched. And if the absolute value, well, technically we should say this. The absolute value of A has to be between 0 and 1. Then we get a compression. Kind of seen that before, just like we did with our absolute value functions. Okay. One other special thing here, C, this value right here, that is actually going to be the y-intercept. Kind of like with our y equals mx plus b, the value at the very end was our y-intercept. Kind of works the same way here. This value c is going to be crossing at the y-axis. So a formula to help us with this. We can find our axis of symmetry by doing the negative b divided by 2 times a. Okay, so again, A is in the front, B is in the middle. Now, when I do this, make sure you always understand B is always attached to X, and then A is always attached to X squared. We are never going to do something weird where, like if we swap the order around, all of a sudden A is just always in front. That's not accurate. A has to be with X squared. So to find our X coordinate of the vertex, we use the above formula. And something I should probably go back and mention. Notice how my axis of symmetry passes right through the vertex there. This value and this value will always match up. Our axis of symmetry is always going to pass through the x value of the vertex here. So that's why when I do the axis of symmetry formula, this is also going to tell me the x coordinate of the vertex. So we can use that to find the x coordinate, then take it and plug it back into the equation to find your y coordinate. This is a way of finding the vertex by just doing the calculations out. So let's take a look how that might look here. First thing is let's identify all of our values. A is a 3. B, notice how there's no x term in the middle. So technically I could call it like plus 0x, meaning B is going to equal to 0 here. And then C is equal to 2. Because this is a positive number, it opens up. And because it's a 3 that's greater than 1, this is going to be a stretched version. So it's going to pull it this way like that. So our axis of symmetry, that is a negative b divided by 2 times a. So in this case, my b is 0. So if I take negative 0 divided by 2 times 3, no real change there because then I get 0 divided by 6, which is just 0. So that's my equation of the axis of symmetry. Now to get my vertex, we're going to take this 0 and plug it back into the original function. So let's take g of 0 here, and that's going to be 3 times 0 squared plus 2. This is 0 squared is 0 times 3 is 0. So, whoops, g of 0 is going to equal to 0 plus 2, which is just going to equal to 2. So this is a vertex. It's a point. So my point is is 0, comma 2. Now, this point is also our y-intercept. So we already just found that. It just happened to work out that way in this case. Okay, so that's all of our characteristics there. Let's talk about the next one. Do the similar thing. So we got A here is a -1, B is a -4, and then I can technically call it +0. So my C is going to be 0 in this case. Since A is a negative number, it opens down. It is a -1, so that is going to be a normal quadratic curve. There's no stretching or compressing. Axis symmetry. Once again, it's x equals the negative b or the opposite of b. So I could say is the negative of -4 divided by 2 times the -1. From there, this is going to turn positive. So I get x is equal to 4 over a -2. And then my axis of symmetry is the equation x equals a -2. For my vertex, I'm going to take this -2, I'm going to plug it back in. So let's find f of -2. So it's negative times negative of -2 squared minus 4 times the -2. So f of -2 is going to be, this will be a +4 here because it's -2 times -2. But then I take the opposite of that. So it's going to be a -4. This is a -4 times the -2 is going to give me a +8. Combine these together, I get f of -2 is a +4. Again, it's a vertex. So I want to write it as an x comma y point. Our y-intercept, if I go back here again, this is a c value is 0. So I could plug in my x equals 0 to always test that out. But my shortcut is it's just 0, 0. It's whatever number is at the end here. Okay, so that's our just analyzing our characteristics here. Now let's take that and plot them. We're going to graph something like this. That process I just did, same thing. Before I get to the graph, I kind of want to think along the same questions here. Label my A, B, and C. Think about the transformations. I don't have to like draw it out yet, but I want to think about it. Find my axis of symmetry, find my vertex, find a y-intercept. It says here plot at least 5 points. I'm going to do something different with that one. I don't like forcing you to plot 5 points. We're going to use some more, especially with the symmetry idea, we're going to make it a little bit quicker for ourselves. First off, like we said, we got A is 2, B is a -8, C is 6. I start thinking a little bit about my transformations. This is a +2, so I know it's going to open up. Okay, it's also with a 2, it's going to stretch. So it's going to get a little bit thinner like this. Okay, so now I'm going to go to my axis of symmetry, which is going to be a negative of -8 divided by 2 times A. So the negative of -8 is going to turn into a +8 over 2 times 2 is 4. So I get the equation x equals 2. Let me show you how this looks. This is my axis of symmetry. At x equals 2, I go here, I'll draw a line that looks like this. This is where it's going to be symmetrical about. I don't know the rest of my vertex yet, but I know it's going to look something like this. Okay. So now I can find the rest of my vertex by doing y is equal to 2 times 2 squared minus 8 times 2 plus 6. Okay. So this is 2 squared is 4 times 2 is 8. -8 times 2 is a -16, and then +6 here. I add all these up, that's a -8 plus 6 is a -2. So my vertex is at the point 2, -2. So I'll plot that right there. If I find a nice easy point, now I could just, from the vertex, I could start plotting in, says 5 points, like normally, like some people like to do, they'll go from the vertex here. They'll go 1 over here, so they'll put a 3 in, they'll put 1 in, then they'll put this one and this one, like in terms of x. You plug in those 4 x values, you'll have a nice curve from that. Me, I like to look for a little bit shortcut. One of the things is that we know the y-intercept is going to be the point 0, 6 because of that right there. So if I plot that point, so 1, 2, 3, 4, 5, 6, that's that one right there. Here's what's nice. I know where my vertex is, and I know one other point that's on the graph. So here's what I can do. Let's use that symmetry idea. If this point is on the graph, then I can go 1, 2 spots over to get to the axis of symmetry. And then I can go another 2 spots away. It has to look like this. The minimum number of points to graph is 3. That's all you need to graph to get this. So I don't necessarily need you to do 5, but if you wanted to, you could. So if you want to be a little bit more accurate and plug in, like, for example, -1, plug that in, see what you get. But personally, I'm good with 3. So it looks like this. Okay. For comparison, I'm going to go ahead and just show you again. The parent function would have looked like this. One, oops, let's here. There, and 1, 2, 3, 4, and 4. This is the parent function. So you can see how some of those transformations work. First thing is the vertex moved to the right and down. And then this is, it's maybe a little hard to see here, but this is actually a little bit skinnier than this one. So that's that vertical stretch idea. So those are the two things that happen. We shifted it right and down. Well, technically 3 things. We shifted it right, shifted it down, and then vertically stretched it. Okay. So talking about our vertex a little bit more, the y-coordinate of the vertex represents either a minimum value or a maximum value, depending on whether the parabola opens upwards or downwards. So what we mean by that is if your parabola looks like this y value is a minimum. If it looks like this, then your y value of the vertex is a maximum in that case. The x-coordinate just represents where, or in terms of word problems, when the minimum or maximum occurs. So determine whether the function has a minimum or maximum and then find it. So in this case, we kind of just look at that a value. That's the only thing that makes a difference about whether it's a minimum or maximum. So since a is greater than greater than 0, we know it opens like this. So this problem is going to have a minimum. Now to find that, we got to just find the vertex. If you're doing graphing, you can find it pretty, like, through some methods there. I'm going to go over by hand. So I'm going to do negative b. So negative of -18 over 2 times a. So that's going to turn into a positive 18 over 6. So x equals 3 here. But remember, the actual minimum value is the y coordinate. So I now need my y value. So y is equal to 3 times 3 squared minus 18 times 3 plus 20. So that's 3 squared is 9 times 3 is 27. This is 30 and 24, so it's going to be a -54 plus 20. So if I combine those, that should be a -27 plus 20 is a -7. So what this means, if I put it all into my language of a minimum and maximum, I would state that I have a minimum of -7 at x equals 3. This is me basically just taking my vertex point. As a vertex, it was the point 3, -7. I'm just interpreting it in terms of that minimum maximum idea. Now, you might go and use your graphing calculators, and there is actually a minimum/maximum feature on there that helps you find that vertex. So if you're doing it graphically, just a couple things to keep in mind. When you go through it, you might get some stuff like this. If you get a value like this where it says the minimum is at -1.999997, that's really close to -2. It's -2. Same thing here. With our scientific notation like e to the -12, that's a really small decimal number, which is basically just 0 at that point. Okay, but that is it for graphing. So TI-84, talk about that some other time. But for right now, just want to talk about how do we graph our standard forms. So for graphing, we want to first find our axis of symmetry. Use that value of axis symmetry to find our vertex. Plot that point with at least one other point. Something easy like the y-intercept would be good, but you can plot any point you want. And I like to just use the symmetry to find another point. All right, that's it for today. Take care, everyone.